Next, we'll be looking at equations and ray diagrams for convex lenses. I'd like to introduce you to the lens equation. 1 over p plus 1 over q equals 1 over f. P is the distance from, and there's a typo here, please correct it, from the lens to the object. Q is the distance from the lens to the image. F is the distance from the lens to the focal point. And R is actually, what I did was I cut and paste this information for mirrors, so we're going to cross out R for now, but you'll find that lenses and mirrors are very similar. What I'd like to go through next is how to draw representative light rays in a ray diagram, and we're going to use these light rays to locate the image that's created by a convex lens. So let's take a look at how this would work. Here's a diagram of a lens. Here's my lens, and right through the middle of my lens is what's known as the principal axis. So there's my principal axis. I can measure P and Q. P is the distance between the lens and the object. Q is the distance between the image and the object. And then F is the distance between F and the lens, the focus and the lens. And what we do to locate the position of the image is this. First of all, you must be given a lens, and you must be given a focal length. You must also be given an object and its location. Based on those things, you can determine the location and size of the image. So let's take a look at how to do that. My first step is to draw a light ray that goes directly through the center of the lens. This light ray will be undeflected or not refracted. It just goes straight through. The second light ray I'm going to draw starts out parallel to the principal axis, and then when it gets to the lens, it bends in such a way that it goes through the focus. The intersection of these two light rays, light ray 1 through the center and light ray 2, which was parallel and through the focus, tells me the location of the image. And if I'm drawing a ray diagram, I can actually create a scale diagram and measure that distance in centimeters if I wish. I can also determine the magnification of the object by comparing the height of the object and the height of the image. So the definition of magnification is the height of the image over the height of the object. So for example, if m were 2, it would mean that the image was twice as tall as the object. And I could simply measure these things to determine that. Let's do some examples. I'm going to have to give you some givens in order to make this happen. You do need a ruler or a straight edge. Actually, you need to measure in this case, so please do that. Now, in this problem, I have given you the foci. They are approximately, it's like 2.9 centimeters, so F is 2.9 centimeters. And now what I need to give you is the height of the object. Let's call that 2 centimeters. And I need to give you an object distance. Let's go with 7 centimeters. So what we're going to do is count out 7 centimeters. I'm going from 11 to 4 on my ruler. And I'm going to make my object 2 centimeters high. And again, one way to determine the location of the image is to draw a ray diagram. And I'm going to draw the same 2 light rays that I showed you in the last example. Now, remember, there are a multitude of light rays coming off of any object that we can see. What we're doing is we're picking two that help us determine the location of the image. What about a light ray that happens to go directly through the lens? It is unrefracted or unbent by the lens. The second light ray that I will consider is a light ray that goes parallel to the principal axis. When that light ray gets to the lens, it will be directed to go directly through the focus. At this intersection is where the image will show up. So this was my object. I had an object distance, P, of 7 centimeters. Now I've determined the location of my image, Q. Let's measure that distance. Appears to be about 4.9 centimeters. And I can also measure the height of my image, which is HI, that's about 1.5 centimeters. Now, you need to be able to solve problems like this with both a ray diagram and with formulas. The lens equation, 1 over P plus 1 over Q equals 1 over F, in conjunction with the formulas for magnification. One formula for magnification is the height opposite the height of the image over the height of the object. You can also get this ratio from negative Q over P. So I'm going to solve for the object distance Q and the magnification with the formula now and verify what I did with a ray diagram. So I'm given P is 7. Q is what I'm looking for. F was about 2.9. If I get out my trusty calculator and solve this, we've got the reciprocal of 7. Nope. That's the reciprocal of 2.9 minus the reciprocal of 7. Take the reciprocal of that. We get 4.95. So Q is 4.95, which is pretty darn close to what we calculated by using a ray diagram. Now I'm going to compute the magnification. I could compute the magnification just by doing negative Q over P. Negative 4.95 divided by 7, negative 0.707. What that tells me is that this image is 0.707, or about 70% the height of the object, and the negative means that it's upside down.